Hello and welcome to today's ACM 6-Off webinar. This webcast is part of ACM 6-Off's commitment to provide value to its current and future members. The ACM 6-Off webinar series features speakers from the Future of Software Engineering track at the International Conference of Software Engineering, as well as select keynote speakers and distinguished paper authors. I'm Robert Dyer, Assistant Professor at Bowling Green State University and member of the 6-Off Executive Committee, and it is my pleasure to welcome you today. Before we get started, I'd like to quickly mention a few housekeeping items shown on the slide in front of you. First, the slides will advance automatically throughout the event. On the bottom panel, you will find a number of additional widgets and resources. If you're experiencing problems with the slides or audio, press the F5 key in Windows, Command R on a Mac, or refresh your browser on mobile devices, or you can close and relaunch the presentation. To control volume, adjust the master volume on your computer. If you have questions during the webinar, please type them into the Q&A box at any time during the webinar, and then click the Submit button. At the end of the presentation, we will have time to respond to questions. This session is being recorded, and it will be archived. You will receive an automatic email notification when that becomes available. Today's presentation is Combinatorial Testing, Progress in Automating Test Design by George Sherwood. George is the founder and CEO of testcover.com, which provides software as a service for combinatorial test designs. Earlier, he worked at AT&T Bell Labs. George has been actively involved in combinatorial testing since 1990. He has found innovative constructions for covering arrays and devised search algorithms for testcover.com. He holds a PhD from Yale University and a bachelor's from Clemson University. George also serves on the board of the Princeton Joint Professional Chapter of the ACM and IEEE Computer Society. George, without further ado, take it away.
Thank you, Robert. Combinatorial testing is a general test design method to verify interactions among test factors. For example, we might want to test some web applications in different configurations with different browsers and operating systems. Each of these test factors has different values which can interact with the values of the other factors. In the example, the web application has different values. These have to work with the browser values and the operating system values. In this pairwise design, the test configurations cover all the interactions between applications and browsers, between applications and operating systems, and between browsers and operating systems. Sometimes combinatorial testing is called combinatorial interaction testing because of this essential property. Here the test factors are for configuration values. They also can be input values, say for describing a use case or the transition in a state model. Combinatorial testing is a general method, but a better description may be that it's versatile. It's been applied to computing platforms, database applications, security, control systems, and environmental effects on system performance. These examples are from presentations at the International Workshop on Combinatorial Testing. Combinatorial testing also is a way to design tests for lots of test factors at once with a small number of test cases. Why would we want to do this? Often there are many test factors, so many that it's impossible to test all the combinations. If there are 30 test factors, say 6 with 3 values and 24 with 2 values, there are more than 12 billion test cases. Combinatorial testing allows us to focus on a much smaller number of test factors. We can design tests that include the interactions among all the pairs or triples of factors using far fewer test cases. In this example, there are about 2,100 pairwise interactions, and they can be verified with only 15 test cases. Our experience analyzing failures supports this approach. Most failures are caused by faults in 1 or 2 factors. Progressively fewer failures are caused by 3 or more factors. Combinatorial test designs are automated. At some point, a button is clicked and the test cases are generated. So humans don't have to work out the combinations among test factors or which interactions are in each test case. An analysis is required, however. At a minimum, the test factors and their values must be chosen. Complex systems require more analysis, of course. Combinatorial testing falls into the category of black box testing. We have requirements for what the system is supposed to do, but our view of it is through external interfaces where we verify that it functions correctly. I plan to talk about a few different topics today. First, I'll introduce some software testing terms so we're all clear on the meaning. I'd like to review where some of the combinatorial testing ideas originated and my experience with a couple of early tools. Conforming to system constraints is essential for tests to verify a system efficiently. I'll talk about these needs and show how constraints can be addressed either with logical expressions or with user-defined embedded functions. I'll introduce embedded functions concepts, including their two types: combination functions, evaluated before test case generation to apply constraints, and substitution functions, which are evaluated after test case generation. As I see it, the benefit of combinatorial testing is test designs that meet objectives efficiently. Embedded functions adds flexibility for practitioners' everyday tasks, verifying classes of expected results and their boundaries. Using a healthcare reporting example, I'll show how more of the test design, analysis, and generation can be automated to improve the control and flexibility of the verification. The International Software Testing Qualification Board, or ISTQB, gives a list of software testing objectives. We want to prevent defects, achieve a level of quality, and meet requirements. The list is general and it applies to any project. But specific projects and their objectives can vary widely depending on what is being developed and the project resources and processes. The variation in project objectives is apparent when we consider software development risk. A product risk is the probability a product will not meet a reasonable quality expectation. When a medical device does not meet expectations, the consequences may be very different than when an entertainment application doesn't work. A project risk endangers the development or test processes of the project. For example, the possibility of a late delivery or delays in defect repair are project risks. Here, the software supplier choice can affect both the risks and costs of the project. The point here is that project objectives and risks vary, so development tools and processes need to reflect that. This is an ISTQB example to illustrate equivalence classes and their boundaries. A savings bank account has different rates of interest depending on the balance. There are 4 classes, and the software is required to behave equivalently for balances in each class. We need to choose the test cases for the software that calculates interest due. A simple test design is to use balance increments of $50, but it takes 19 test cases just to cover 2 classes. A more efficient design is to test a balance in each class 1 and test the class boundaries. There are far fewer test cases. Each of the 4 classes has an interior test value, and each of the 3 boundaries has 2 values, one in the lower class and one in the higher class. Equivalence classes and boundary values are fundamental constructs used by test practitioners to make the design and execution efficient. The origins of combinatorial testing began almost 100 years ago. The ideas of these 3 people, Fisher, Rao, and Taguchi, enabled combinatorial testing. Ronald Fisher was an English statistician and biologist. In the 1920s, he worked at the Rothamsted experimental stations analyzing data from crop yield experiments. For example, experimenters would test different kinds of fertilizer to see what worked best. While he was there, Fisher created the theory and methods to do the analysis. He invented statistical techniques for the analysis of variance, maximum likelihood, and much more. He literally wrote the book on the design of experiments. Kalyampudi Radhakrishna Rao was Fisher's student at Cambridge. Rao studied and introduced orthogonal arrays in the 1940s. Since then, orthogonal arrays have been used more and more to design experiments for agriculture, manufacturing, clinical trials for new drugs, and market research. Orthogonal arrays are powerful tools for discovering the effects of test factors and how they interact. In the 1950s, Shinichi Taguchi began to work on improvements to quality and reliability in manufacturing. He collaborated and consulted widely, working with Fisher for a time at the Indian Statistical Institute. Taguchi's use of experimental design was innovative and sometimes controversial. Overall, his ideas have had an extensive influence in improving manufactured quality. The orthogonal arrays were an essential part of this work. What's an orthogonal array? It's a template for test design. It has n rows, which correspond to test cases, and k columns for test factors. This example array has 4 rows and 3 columns. Each factor can take 2 values, either 0 or 1, so the number of values v is 2. The strength T of the array is 2. This means that any 2 columns contain all pairs of values equal number of times. In the first and second columns, we have the values 0, 0, 0, 1, 1, 0, and 1, 1. These pairs of values identify the interaction between the first and second test factors. This array has 3 pairs of columns, first and second, the first and third, and the second and third. It's easy to see that each pair of columns contain all 4 pairs of 0 and 1 exactly once. So a test design using this template can cover all the pairwise interactions of the test factor. For a strength 3 test design, we need to include all 3-way combinations of columns. When there are 3 test factors, the factors have only one 3-way combination, and the array needs 8 rows to cover all 3-way interactions. For describing systems in the real world, we need arrays that have factors with different numbers of values. These are called mixed arrays. In this notation, there are K1 factors with V1 values, K2 factors with V2 values, and so forth. The properties of orthogonal arrays are important for verifying the interactions of test factors with each other. A test plan based on an orthogonal array can verify the interactions among any key factors. By the 1980s, people began to work out the experimental design ideas for testing software. Seizo Tatsumi at Fujitsu described the use of orthogonal arrays and covering arrays to generate test cases. Robert Mandel at Softtech used orthogonal Latin squares to design compiler tests. Taguchi visited Bell Labs and began a collaboration with Madhav Phadke. Taguchi's methods gained acceptance at AT&T and inspired Bob Brownlee, Jim Krauss, and Madhav Phadke to come up with the orthogonal array test system, or OATS. I was at Bell Labs then and had no idea any of this was going on. I was supervising a system test team responsible for a family of new local area network products. StarLAN hardware would be the first products to use Ethernet, CSMA, CD protocols on telephone cables. StarGROUP software would offer file and printer sharing over the network to improve office productivity and reduce costs. We had what we called a client installation test. It included installation and some operational tests, and it was here that our extensive configuration requirements hit us. The job was large and labor-intensive. We had to support 101 combinations of keys and operating system versions with 15 different network cards. It was then that I heard about OATS as a possible way to reduce the number of test configurations. Unfortunately, oaths didn't work for us. We had complex configuration constraints which disallowed some of the test factor combinations. And some of the configurations that oaths generated were these impossible test cases. Instead of trying to describe 1990 technology here, I'd like to illustrate the problem with a browser example. Here we need configurations to test 3 applications using Windows and Linux operating systems and 3 browsers, Chrome, Firefox, and Internet Explorer. The test cases came from an orthogonal array. The 9 rows cover all pairs of factor values. The problem is that the Linux Internet Explorer configuration is invalid. It is not supported and cannot be tested. What can we do to fix the plan? If we skip the test case, there are 2 valid interactions that will not be covered. Linux with F1, Internet Explorer with F1. The situation gets even messier when there are more test factors and more complicated constraints. The conclusion I reached at the labs was that a search was needed and that it should be restricted to allowed combinations only. We used these ideas when I prototyped the CATS test case generator. What CATS did was search among the allowed test cases to handle constraints of the system under test. It looked for a sequence of tests, minimized the number of uncovered pairs, and it did this simply by choosing the next best test case on the way to the minimum. CATS used a greedy search algorithm for mixed arrays with constraints. It took advantage of the computer's speed to select a small number of test cases. CATS was updated to allow designs with higher strength. It was distributed within AT&T, and after some study, its use was dubbed the best practice. The motivation for CATS was to find test cases that were practical to use, but we also found that typically CATS generated fewer test cases than oaths. The reason for this was that CATS was looking for covering arrays, not orthogonal arrays. What's the difference? An orthogonal array contains all pairs an equal number of times. This balanced property is useful for measuring the effects of factors and how they interact. However, for pass-fail results of software functional testing, we don't need the arrays to be balanced. Instead, covering arrays contain all pairs at least once. Consequently, covering arrays can be smaller than orthogonal arrays. This means they lead to fewer test cases. There are different types of needs for constraints. We just saw how 2 valid configuration values, Linux and Internet Explorer, are invalid together and can mask valid configurations. The same thing can happen with input values. Here we have 3 valid factor values for a date. They're month, day, and year. Taken together, they're invalid because 2019 is not a leap year. Constraints are also needed to include valid combinations that might not be covered otherwise. Typically, testers need to verify classes of expected results. Constraints can steer the design to cover the classes. We'll see examples of this shortly. Over the past several years, researchers have had some success incorporating constraints in combinatorial design. Often they are specified by logical statements to be satisfied during test case generation. In the browser example, this statement specifies the OS browser configuration constraint. Alternatively, with embedded functions, the browser values can be represented as an fbrowser function. The function's argument is the operating system value, Windows or Linux, which determines the browser values. In this example, we want to verify an equivalence class of system responses for valid calendar date input. We want to check class boundaries for the first and last day of each month in the years 2019 through 2021. Here's a list of the input factors. We have the 12 months. There are values for the first, 10th, and last days of the month, so we can verify an interior day and the boundaries. calendar of the 3 years. The maximum day value is constrained. It depends on the month and year values. In fact, the month and year values determine the maximum value of the day factor. Here's one way to represent the calendar constraints. They are specified by logical statements to be satisfied during test case generation. The first statement says that the long months can have days 1, 10, and 31. The second statement has the corresponding values for the short months. The last two statements give the day values for February depending on whether the date is a leap year. Constraints can be converted to forbidden tuples, which are combinations to be disallowed during test case generation. Logic solvers also have been used successfully in test case generation. Conforming to real-world constraints in complex systems can be challenging. As a software engineer, I haven't been satisfied with the ways constraints are specified. It seems that a simpler way, better aligned with programming, would be more usable for practitioners. This led to the idea of embedded functions. They offer an alternative with dependent factor values represented as functions in general-purpose programming language. Here we're using PHP, which is widely used in online systems. With embedded functions, we're using functionally dependent relations to apply constraints among test factor values. This means that one or more values of a dependent factor are identified by other determinant factors. The determinant factor's values apply some or all of the dependent factor values. The relation is like a math function, mapping its domain to its range, or a programming function comparing return values from its argument. The calendar example illustrates an embedded combination function in which the last day of any month is identified by its month and year. So combination functions define constraints for test case generation. Last day function is an example of a combination function. When the last day function is evaluated for a month-year pair, it returns the value for the last day of that month. More generally, a combination function can return a list of allowed values for the generator to use. If the combination of determinant values does not have any dependent values, no value is returned. The generator calls the functions for all combinations of arguments and uses the resulting values to generate conforming test cases. So we need a last day function. It's easy to write one for the given years, but it's even easier to reuse a built-in function that has already been tested. This last day function converts month strings to integers and uses them to call the PHP function cal days in month. Substitution functions are evaluated after test case generation. Each substitution function just returns a value for a factor in its test case. The substitution function's value is determined by other factor values in the test. These functions have a variety of uses, but the one I want to talk about is the evaluation of expected results classes. Testers use equivalence partitioning for input and configuration test factors routinely. Valid and invalid classes can be identified, and members of the classes are used in the test design for input and configuration values. But here I'm talking about equivalence classes of system behavior, which is different. To verify system behavior, we need to identify classes of expected results. Substitution functions can identify the expected results class for each test case. They can do the evaluation automatically, which can improve convenience and accuracy. The evaluation can enable an assessment of equivalence class coverage by the test cases generated. Generally, equivalence class functions, either combination functions or substitution functions, help to manage verification of results classes in combinatorial testing. I'm I'm going to use a body mass index report application to illustrate these ideas. The BMI is the health measure to classify people as underweight, normal, overweight, and so forth. Here's a summary of the requirements. R1. There are 5 input factors: age, weight, height, sex, and intake. All of them are integers except for sex, which is female or male. R2. Body mass index, or BMI, is the weight divided by the height squared. The 703 converts to standard units, kilograms per meter squared. R3. If age is 65 years or older, a Medicare report will be generated. If age is younger than 20 years, a child report containing the BMI percentile will be generated. The adult classifications are not used for children. Different tables are used for boys and girls, so there are 2 types of reports generated. R5. If age is 20 years or older, the adult report will be generated for the BMI classification. There are 4 BMI ranges, leading to 4 types of reports. If the BMI is less than 18.5, the underweight report is generated. If the BMI is between 18.5 and 25, the normal report is generated, and so on. Equivalence classes are a basic test design technique to organize expected results into similar classes. In our example, we want to verify the underweight report is generated when the age, weight, and height values require it. We can verify the underweight report with a few test cases in its equivalence class and at the class boundaries. In the example, the Medicare, child, and adult reports each have multiple valid equivalence classes. It's valid for the Medicare report to be generated or not based on the age value. The child report can be generated in the boy class or the girl class, or not at all. The adult report can be generated in any of the BMI classes or not. To sort this out, use the equivalence class factors, 1 for each report. The value of the factor is the equivalence class for the associated report. In a deterministic system, the equivalence classes are functionally dependent. Input and configuration values determine the result, and the result is a member of 1 or more equivalence classes. So each of the 3 reports has an equivalence class factor, and each of the factors gets its values from an equivalence class function. The equivalence class functions are very simple. Here's the Medicare report function. It returns yes or no based on age. The child report returns girl or boy according to the sex value if age is between 0 and 20. Age value is greater than or equal to 20, it returns no. The adult report function calls the BMI function to get the BMI value. Then it returns the BMI classification if age is greater than or equal to 20. For younger ages, it returns. That's it. We need input values for the test design. The weight and height value should result in all 4 BMI classifications. It turns out that we can do this with 2 weight values, 2 height values, which will be paired. This graph of BMI boundaries, the horizontal axis is weight, the vertical axis is height. The 4 points shown are in each of the BMI classifications. Their weight values are 120 and 190 pounds. Their height values are 64 and 71 inches. The weight-height pairs is in a classification. This slide shows the factors and values for the BMI example. The names that start with a $ sign are PHP variables to be used as equivalence class function arguments. There are 5 input factors with fixed values for age, weight, height, etc. After the input factors are 3 equivalence class factors for the 3 report types. For the age factor, we choose 15, 42, and 67 years to generate the child, adult, and Medicare report types. We use the weight weight and height values from the previous slide. The sex values are female and male, and the intake values are 2,000 and 3,000 calories. The values for the equivalence class factors are given by the equivalence class functions for the report. Substitution functions, so they're evaluated after test case generation. They do not affect the test inputs, just compute and return the expected results classes. This design contains 6 test cases which cover all the equivalence classes, but it happens accidentally. If we use the same design with the age values in a different order, we still get 6 test cases, but they don't cover all the equivalence classes. Let's look at test cases. Here are the test cases for the first design. Input values are shown, and their strength 2 interactions are covered. The expected equivalence class values are computed as shown on the right. We can see that the classes are covered for all 3 report types: 2 for Medicare, 3 for child, 5 for adult. The second set of test cases has the same input values, except for the age factor. The age values are rotated into a different order. The other input factors have corresponding values in both sets of test cases. Both sets of test cases have pairwise coverage. But now, when we check the equivalence class factors, there are 2 classes missing. Underweight and obese for the adult report are not there. So how did this happen? Let's look at test case 1 in the first set of test cases. Medicare report depends on just one factor, age. Test case 1, age and the Medicare equivalence class are shown in bold. All the age values are covered in both sets of tests, so all the Medicare classes are included. Child report depends on 2 factors, age and sex. All pairs are covered in both sets of tests, so all the child equivalence classes are here too. But the adult report depends on 3 factors, age, weight, and height. Pairwise coverage does not guarantee coverage of all triples. Might be included, or they might not. These test cases illustrate both outcomes. At this point, we might go to a strength 3 design for the coverage, but we're going to use equivalence class combination functions instead. Functions constrain a test design to cover classes of expected results, even when T is less than L, when the strength is less than the number of adult determinant factors. This design has the same input values, but now we're using equivalence class combination functions. They're the same functions, but they're evaluated before test-based generation, not afterwards. The equivalence class functions return expected results classes from the determinant factors. The function is evaluated for all combinations of its determinant values. For example, the adult report function is evaluated 12 times for 3 ages, 2 weights, and 2 heights. These valid combinations conform to the equivalence class constraints and are made available for the test case generation. Every allowed equivalence class value must appear in the pairwise design in at least one test case with a combination of its determinant factor value, and the equivalence class value is paired with the other factor values as allowed by constraint. We get 14 test cases in this design. All the pairwise interactions and input factors are covered, and all the classes of expected results are covered. Also, the pairwise interactions of each equivalence class factor and its non-determinant factors are covered. Here's an example to explain that. Let's look at test cases 1 and 7. These 2 test cases are in the adult overweight class. The adult equivalence class factor is determined by the age, weight, and height values, so the other 2 input factors, sex and intake, are non-determinant. The values of sex and intake are paired with the overweight class in these test cases. Test case 1 is paired with female in 2000. Test case 7, overweight, is paired with male in I'd like to show how verification of boundary values can be applied to this example. An input factor like age has values that are ordered. It has a minimum value, a maximum value, and values in between. In contrast, sex values are enumerated. There is no ordering. Maximum and minimum age values are edges. Extreme values can be included in test design, but this example focuses on boundary values. When factors are ordered, and when they determine equivalence classes, developers must implement the boundaries. There are work areas where errors are introduced sometimes. In my example, there is an age boundary between Medicare classes, and another one separates both the child and adult classes. We can generate test cases to verify the age boundaries by replacing the previous internal values with boundary values. 19 is the maximum age for the child report, 20 is the minimum age for the adult report, 64 is the maximum age for no Medicare report, 65 is the minimum. This design uses the 4 age boundary values. Otherwise, it is the same as the previous design. Medicare, child, and adult equivalence class factors continue to use combination functions, so the test cases are constrained to cover the expected results classes. Now we get 18 tests. They have been sorted by age to show the boundaries. The Medicare report classes are above the top boundary. The adult classes are above the lower boundary. And the child classes are below that. All the pairwise interactions are covered. That was easy. It suggests a question. Can we cover the values at the BMI boundaries? The answer is yes. We can choose the weight and height input values for patients whose BMI values are on the boundaries. We'll use one embedded function to test it. Here's the formula for the BMI in terms of the input factors, weight, and height. What we need is input values that reach the BMI boundaries. Let's try the weight input. If we solve the equation for weight, we can express its input value in terms of the height input and BMI boundary value. Here's how it can work. We'll continue to use the height values, 64 and 71 inches. And we'll introduce a BMI boundary factor to specify which boundary to use. Here's one more detail. The weight input needs to be an integer to generate either the minimum BMI value for the higher class or the maximum BMI value in the lower class. We'll introduce an input limit factor to specify which limit to use. This weight boundary function specifies the input values for the weight factor. From its arguments, we can see that it depends on height, BMI boundary, and input limit factors. It uses the weight formula above, rounds up to the next integer. This value is returned for the minimum value in the higher BMI class. The next lower integer is returned for the lower side of the boundary. This is a graph of the allowed BMI boundary values for this example. Weight boundary function has 3 arguments, height with 2 values, BMI boundary with 3 values, limit with 2 values. Their product leads to 12 weight input values. The weight values are in a 1-to-1 correspondence with 12 patient BMI boundary values, like 18.4 or 30.1. These are the values the system under test should compute from the patient weight and height input. They're not the exact values, 18.5, 25, or 30. Now, the patient BMI is not a test factor, but because of its correspondence with weight values, we know that when a weight value is associated with the value of another factor, the corresponding patient BMI value is associated also. Design has 2 new factors, BMI boundary, input limit. And instead of fixed weight values, we're using the weight boundary function It's a combination function, so it's evaluated for all combinations of arguments. The weight values are paired with the other factors, including the age boundary values. There are 4 age values, 12 weight values, so there are 4 times 12 or 48 pages. Each weight value corresponds to a unique patient BMI value, so the boundary values for age and BMI are paired. So we're pairing the values of 2 intersecting boundaries. There's one more design change. The equivalence class functions are substitution functions. We don't need them to ensure coverage of the results classes because the boundary value factors are doing that. Instead, the substitution functions just identify the equivalence classes for each test case. The design has 48 test cases. Here are the first 24. Let's take a look at how test case 15 is constructed. The weight value 132 comes from the weight boundary function, evaluated for a combination of determinant factors. This test case uses height 71, BMI boundary 18.5, and limit max. In this test case, the weight is paired with non-determinant values for age 64, sex female, and age 3000. From these values, the equivalence class substitution functions tell us we should not expect a Medicare report or a child report, but there should be an underweight report. And here are the rest of the test cases. Here's another way to view the same test cases. They're the test case numbers 1 to 48, organized by age and BMI boundaries. There are 2 sections. Height 64 is below, and height 71 above. Age boundaries are the horizontal line, increasing from bottom to top. They show the child-adult boundary and the Medicare boundary. The BMI boundaries are the vertical line, increasing from left to right. There is the underweight normal boundary at 18.5, normal overweight boundary at 25, and so on. When we pair the values of 2 boundaries, we're covering the interactions between them, so we can verify their corners. Let's look at the upper left corner. Test cases 15 and 36 have age 64 in the Medicare report no class. Test cases 28 and 10 have age 65 in the S class. Test cases 15 and 8 have weight of 132 and an underweight BMI of 18.4. Test cases 10 and 36 have weight 133. That's 1 pound more for a normal BMI of 18.5. The term corner case is a real software engineering term. It has a pathological connotation because it depends on multiple factors having specific values. They may be difficult to identify and verify. But this automated design covers all the Age-BMI corners, and it includes the allowed interactions for the other factors not shown here. As I mentioned earlier, test objectives can vary a lot. So verifying all 48 corners may not align with test objectives. Can we design tests that verify a useful subset? Yes. In this example, all we have to do is specify the weight boundary function as a substitution function rather than as a combination function. During test case generation, its determinant values are specified in each test case. The weight input values are evaluated from those arguments in. This design has 12 test cases instead of 48. Here's the corner map for the same test cases. Now we're covering 25% of the corners. This sample represents pairwise coverage of the 4 factors in the map: age, height, BMI boundary, input limit, not weight. Placement of the test cases on the map illustrates the coverage. For example, age, height interactions are covered because it's a test case in every row. BMI boundary limit interactions. BMI boundary input limit interactions are covered because there's a test case in every column. The other pairings can be. We've seen many valuable improvements to combinatorial testing over several decades. I'm particularly excited about the potential for embedded functions to advance the practice further. Efficiency, flexibility, and automation are needed. We live in the 21st century with the Internet of Things. Every day we become more dependent on software, networks, and distributed applications. We have more features and complexity, shorter development cycles, more reuse of components. We have to keep. Let's move on to questions and answers.
All right, thank you, George. Our first question is essentially saying, what advice can you give the average software developer so that the code that they're writing can lend itself to being more easily tested with the techniques that you discussed today?
It's a good question, and frankly, I'm not sure that there is something specific that wouldn't already be a good practice in terms of designing the code that you're working with. And I say that because my experience has been that combinatorial testing is really general and versatile. So I think if you're using good practices, you're probably pretty much as far as you can go with respect to trying to do it if you're designing so that it can be tested. Clearly, this is one tool among several. It's using a black box model, and that that's a limitation right there. So if you're doing other things, coverage for your unit tests and so forth, those all complement this. And this is the sort of thing that you probably use in complicated integrations or in tests involving the integrated system as a whole. I don't know whether that helps answer the question, but I think you really need to use it where it's most needed and complement it with other tools that can deal with other parts of the development process.
So throughout the talk, you mentioned the use of embedded functions to essentially help with the testing strategy here. How do you test an embedded function itself?
I don't have a different answer for that other than it's code that you test. One thing that you notice, I hope, in the talk is that these are very simple functions. And so they shouldn't require an extensive rigor in order to. You want to keep things simple and hide information, and do all the good software practices that are useful here. And once you have an embedded function that works, you can reuse it. In many cases, there are existing PHP functions that can be reused, as I illustrated. And in terms of the implementation that we have already, we have a rather simple HTML-based forms interface where you can put in a function, and it gets scanned to make sure that it's using allowed functions that we know are safe. And it is, again, in this initial implementation, what we've done is we've required that the function can, in fact, return values in order to be able to use it in the tool. But this is a tool, and there are things you can do that maybe aren't going to do. If you make mistakes using any tool, then it's not going to do what you want. And so there are notices and diagnostics that go in here, but that's beyond the scope of the talk. So it's really a question, I think, of getting experience, and then you can see how much testing is needed or not needed with respect to the functions themselves. Okay. You discussed quite a few interesting techniques today.
do you have any recommendation on specific tools that actually implement these techniques? For example, the ACTS tool from NIST.
Yeah, ACTS is a tool that is distributed by NIST. Its origins are in research. Lee has pioneered a lot of that work. That tool doesn't use embedded functions, but it does do much of what I've been describing here. The only tool that I know of that uses embedded functions is testcover.com. That's been one of our research efforts, and it is available. It's implemented, and people can try it. Did that answer the question, or did you want more?
Yeah, lots I think that answers it.
Just another quick comment on that. If you're interested in the extent of tools, there are lots of them. If you go to pairwise.org, it's a website that was created and maintained by Jacek Czerwonka from Microsoft. There's a fairly lengthy list of various tools that can do various combinatorial test designs.
So we did get one question asking specifically if there's anything you have to handle special when dealing with inputs that are floating point.
When I think of combinatorial testing, I think of typically a small number of values, small being a relative term, for any particular factor. So in that sense, we're talking about discrete numbers when we look at how things are interacting. You might have floating point numbers, and there may be 3 of them, 10 of them for a particular factor. And the way the tools typically treat these is they're discrete values for the purpose of the combinatorial test case generation. So, for example, in test cover, you are dealing with strings of inputs which are compared as values for the factors, and then integers are used in order to actually do the computation to get the combination. When you're using embedded functions, type becomes more important because you've got a program that's actually trying to interpret things correctly. So it's a little bit different with the embedded functions. But I don't see floating point numbers or values that aren't that aren't strings or integers. It really doesn't. It shouldn't matter. The kind of testing where you really have to consider what's going on with floating point numbers, in my experience, hasn't been this kind of testing. It's been situations where you've got to look out for underflow or overflow and make sure your accuracy is okay. But that's a totally different situation. So the short answer here is, yes, you can use fixed point or floating point numbers, and you probably want to make sure that the numbers of any particular factor value aren't so large that you're going to end up with way too many test cases.
So what role, if any, does randomization play in the generation of a combinatorial test suite?
None. Not, and that's kind of terse. But you can, for example, if you don't care about an answer, you don't care what a value is in a particular test case, you can set up a substitution function which puts a random value in, or one of some number of values that you want to select from. But random values, I think, are good for certain applications, testing applications where, for example, you may be running a load for some period of time and you don't want to just use the same inputs over and over again. And their random testing may be useful. But when you're doing combinatorial testing, you're actually looking at test cases which are more compact than random testing, random values. if you were to pick random values and do a combinatorial test, you're probably going to find that you can get better coverage. I mean, people have studied this. You can get better coverage with fewer test cases by using combinatorial testing because you're actually selecting the values that are going to give you fewer test cases rather than just selecting them randomly.
So do you have any advice for any shops that are currently doing a test-driven development strategy and they want to essentially integrate combinatorial testing in? Is there anything special that needs to happen, or is it just simply plug right in?
I'd say try it. Start with a small example and see how it works for you, and then build on that. I mean, that would be my advice for any application of it. It takes some familiarization to figure out how to get the most out of it, and just jump in and try it a little bit. See if it complements some of the testing you're already doing.
All right, I think we have time for one last question. So when we look at combinatorial testing, somebody was wondering specifically, could this be applied in the area of security testing?
Yes, in fact, it has been. Early on, I had a slide about cross-site scripting. That particular example, a combinatorial design was used to select parameters to actually generate a penetration test. And it has been used that way, yes. I don't know, I haven't thought about security testing specifically with respect to combinatorial testing enough to have an opinion that's strong here, but I know it has been done. And if somebody would like additional information on that, I can point you to people who may know more about that than I do.
All right, thank you very much. I'm afraid we've run out of time today, so I'd like to thank George again for his informative presentation and his insightful answers to the many questions. Special thanks to each of you for taking the time to attend and participate in today's webinar. This webinar was recorded and will be available online in a few days at www.sigsoft.org/resources/webinars.html. You can find announcements on upcoming ACM and SIGSOFT webinars and other ACM activities at learning.acm.org and www.sigsoft.org. On behalf of SIGSOFT, the speaker, and myself, thanks again for joining us, and I hope you'll join us again in the future. And this concludes today's webinar.